Welcome. This is a lecture about the inclusion-exclusion principle. We're going to be explaining it mostly in the context of the subject of derangements. So the question is, how many ways can you arrange a 20-volume encyclopedia? If anybody remembers what an encyclopedia is, a 20-volume encyclopedia on a shelf such that no book is in the correct place. So that is to say, the books are numbered 1 through 20, and you want book number 1 not to be in the first place, and book number 2 not to be in the second place, and so on. So that's the question. And this is called the derangement number. And we're interested in figuring out the derangements of n, in particular derangements of 20. So these numbers are written d, or d sub n. If you flip the question around, you can ask the following: what are the arrangements of the books such that at least one book is in the correct place? So one book could be correct, or two books could be correct, or they could all be correct. And if you think about it for a second, call that number n. That's clearly the complement of d, which is to say, if you look at all permutations of 1 through 20, well, let's see. A permutation either is a derangement, which is to say no book is in the correct place, or it has at least one book in the correct place. And this notation here means disjoint union. And so that says that all permutations, which is 20 factorial, is d plus n. So if you figure out one of these numbers, you've figured out the other. And we're going to figure out n primarily, and then say that d is 20 factorial minus n. Okay, so let's label dn the derangements of n. And for example, let's see, d3. So you have 1, 2, and 3. How many ways are there of arranging them such that no number is in the correct position? Well, let's see, 1 has to go either in position 2 or position 3, so let's put it in position 2, and then I can't put 3 there, so I'm forced to do this. Or another option is I put 1 here, and then I'm forced to put 2 and 3 in like this, so that says that d3 is equal to 2. Let's see, how about d4? So I can put 1 in one of 3 places, so let's say we put 1 in position number 2. Now 2 I can put in any of the remaining 3 places. So I could do this, or I could put 2 here, and then I'm forced to do 4, 3, or I could put 2 in the last place, in which case I'm forced to do 4, 3 like this. And let's see, if I put 1 in the third place, well, then how many places are there to put the 2? Let's see. In this second column, what I'm going to do is I will get, there are 3 different places to put the 3 in this setting. And once I've put the 1 in the 3, then the 2 and the 4 are forced. And similarly here, I have 3 different places I can put the 4. And so d4 is equal to 9. But it's not easy to figure out these numbers directly. I certainly don't see a pattern yet, and if you do d5, it just gets more complicated, and it's not so easy to count. So what we're going to count is this number n instead, which is the complement, the number where at least one number is correct. So for example, when n is equal to 3, how do you count that? So, well, 1 could be correct. How many ways are there to have 1 be correct? Well, if you put 1 in the right place, 1 could be correct, or 2 could be correct, or 3 could be correct. So I have to count each of these. Well, how many ways can 1 be correct? You put 1 in the right place, and then you have 2 factorial ways to do the remaining ones. similarly for 2, and similarly for 3. And so it looks like there are 6 ways of having at least one number correct, but of course that's ridiculous, because 6 is the total number of permutations, and the point is we've counted this one several times. Okay, well, how do we account for this? So it's going to be 6 minus 3, and the 3 is because of this 1, 2, 3 counted 3 times, but let's look a little more closely. The point is, how many ways could I have at least 2 numbers in the correct position? Well, I could have 1 and 2 be correct. That happens here, here, and here. Or I could have 2 and 3 be correct. That happens here, here, and here. Or I could have 1 and 3 being correct. And that happens here, in the same place again. Here, here, and here. So these 3 entries account for the permutations in which at least 2 numbers are in the correct position. So I'm going to think of this as being 6 that's the number of ways of greater than or equal to 1 correct, and then I have to subtract these 3, which is the number of ways greater than or equal to 2 can be correct. But then I've subtracted too much, because I have to add back in 1 to take into account this 1, 2, 3, where all 3 are correct, and this number comes out to be 4, which is correct. So the number of arrangements where at least one number is correct is 4, and that plus the number of derangements, 4 plus 2, is equal to 6. So this is the inclusion exclusion counting here, this alternating sum, which gives me the right number. Okay, let's go over that again. I want to explain how to properly take into account these overlaps. So it's really helpful to draw a picture here, and imagine that we have 3 sets, S1, S2, and S3, and they're not necessarily disjoint. And I'm interested in counting the number of elements in the union. So you draw the union of these 3 sets like this. Here's S1, S2, and S3. How do I count the number of elements in the union? Well, sort of as a first approximation is you add up the number of elements in S1 plus the number of elements in S2 and the number of elements in S3. And if the sets were disjoint, that would be correct, but S1 intersect S2 is this red region, and you've counted that twice, so you have to subtract it off. And similarly, you've counted this region, S1 intersect S3 twice, so you need to subtract that off because of overcounting. And finally, S2 intersect S3, you've counted twice, and you subtract that off. And now you're very close to the right answer, though, except that right in this middle region here, it has 3 colors in it. Here's the red, blue, and green regions, and this middle region has all 3 of them, and you've subtracted it off 3 times, and that's too many, so you need to add it back. And that is the correct way to count the number of elements in this union. This last term, if you look in the middle region, you've counted it 3 minus 3 plus 1 times is the correct number of times to count it. So that, in a nutshell, is the principle of inclusion and exclusion. So let's look at it in our example. We're going to take S1 to be the number of arrangements or permutations of 1 through 3 such that 1 is in the correct place. So the number 1 appears in the first position. And similarly, S2 are the ones where the number 2 appears in the correct position, and similarly S3. And this number n that we were talking about is the union of, it's the number of elements in the union of these 3 sets. which is to say these are the permutations where at least one number is correct in the correct position. So that is this number n that we're interested in counting. So the number of elements in this union by this principle is the sum of these three minus the intersections, and then you have to add back in the intersection of all three. And in this first term I wrote unions, but of course those are supposed to be pluses. And then the last term is you add back in the intersection. So what does that say? What is S1? That's the permutations where 1 is correct. There are 2 factorial of those, and similarly 2 of those and 2 of those. That's our 6 right there. And then what's S1 intersect S2? Well, that's where 1 and 2 are in the correct place, and then, well, 3 is forced, and so there's only 1 of each of these. And then, of course, the last one is where everything is correct, so there's 1. So the number is 6 minus 3 plus 1 is equal to 4. And that's the number that we saw earlier. Okay, so let's just check one last time. Here are the 4 permutations of 1, 2, 3, where at least one number is in the correct position. So, okay. So that leads us to the first statement of the inclusion-exclusion principle. I'm going to call this inclusion-exclusion version 1. And it says the following: suppose you have n sets, finite sets, S1 through Sn, and I'm interested in calculating the order of the union. Well, there's a formula, and the first term is the sum of the orders of each of the Si's. And then you have to subtract off the order of S1 intersect S2 and S1 intersect S3 and so on, all of the orders of pairs, intersections of pairs of sets. But then you need to add back in all the intersections of triples and then subtract off quadruples and so on all the way down to the end. So let's write the theorem. This is inclusion, exclusion. This is version 1. It says that the order of the union of S1 through Sn is the following alternating sum. So you first add up the orders of all of the SI's, and then sum over I and j and subtract off the intersections of all pairs, and then add back the intersections of all triples, so that's sums over I, j, and k, distinct, of course. And all the way down to the very last term, which is minus 1 to the n plus 1 times the order of the intersection of all of the sets. And that is, that's the inclusion-exclusion formula. Okay, so let's go back and look at our example from the beginning. What are all of the permutations of 1 through n such that at least one number is in the correct position? So again, either number 1 occurs in the first position or number 2 in the second and so on. So this is this number n from the beginning, and it's once we figure out this, we'll know the derangement number also. And how do we think of this in terms of inclusion-exclusion? Well, let Si be the set of permutations where number I is occurring in the correct place. So that is to say, number I appears in position I. Okay? So then clearly this n is the cardinality of the union of these sets. N is the cardinality of S1 union ... up to Sn, where because it's at least one is in the correct place. So that is to say, when you have a union, you think of it as being number 1 is correct, or number 2 is correct, or dot 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 number n is correct. And so this is the number that we want to calculate. And so by inclusion exclusion, we write it as this alternating sum. So it's the summation of the order of SI minus the summation of the orders of the intersections of pairs plus intersections of triples and so on. Now, what is the order of SI? Excuse me, the intersection of k of these sets SI. So you have k numbers I1 through IK. So there's k of these sets. What's the order of this intersection? Well, this means that I1 is in the correct place and I2 is in the correct place and dot 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 up to IK is in the correct place. So that is to say, you put these k numbers in to their correct places, and the number of such permutations is, well, you're allowed to arbitrarily permute the remaining terms. So you've fixed k, and the order of this intersection is n minus k factorial. So, for example, the order of S1 is n minus 1 factorial. What about for example, the order of S1 intersect S2 intersect S3? That's the permutations where 1 is correct and 2 is correct and 3 is correct. So 1, 2, and 3 are correct. And what's left is n minus 3 factorial. Okay, so that tells us how to calculate the orders of each of these intersections. So the order of SI is n minus 1 factorial. The order of SI minus intersect SJ is n minus 2 factorial, and so on. And the order of the very last one is 0 factorial, which is 1, where every number is in the correct position. Now, let's write down the formula for n. Well, the first term is n minus 1 factorial. And how many of these terms are there? Well, I is running from 1 to n, so it's this number times n. From here, there are n of these i's. Okay. Now, what's the next term? You have to subtract off here, this is the intersections of pairs, so we have to subtract off n minus 2 factorial, and how many terms are there? Well, it's pairs ij, and so how many are there? That's n choose 2. Good. The next term is we have to add back on n minus 3 factorial times n choose 3, and so on, all the way down, alternating pluses and minuses. And then the last term is going to be n factorial, 1. And so the formula is the summation over k of minus 1 to the k plus 1, that's the sign, n minus k factorial times n choose k. And k is running from 1 to n. So that's the formula for this number of permutations where at least one of the numbers is in the correct position. Okay, let's see if we can simplify this. Well, so it's the sum over k, minus 1 to the k plus 1. And here you get n minus k factorial times n factorial over k factorial, n minus k factorial, and isn't that handy? These terms cancel, and you get summation minus 1 to the k plus 1, n factorial over k factorial. Isn't that nice? And let's see, we can factor out the n factorial, that's just fixed. So what you're getting is n factorial times summation minus 1 to the k plus 1, 1 over k factorial. And I'll just write that as n factorial, let's see, times we're starting at k is equal to 1. So the first sign is plus 1 over 1. So you're getting 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial and so on down to plus or minus 1 over n factorial. So that is the number of arrangements where at least one number is in the correct position. Okay. Okay, so now let's go back and look at our derangement number. So remember the number of derangements plus this number n that we're talking about is n factorial. So that is to say the derangement number is n factorial minus n. And so we can write that out like this. And if I just combine the two terms, I get n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial and so on down to the last term is plus or minus 1 over n factorial. These first two terms cancel and give 0, but it's a little bit nicer just to keep them like this. So that gives us the following theorem. The nth derangement number is n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial down to minus 1 to the n times 1 over n factorial. And this is a misprint here, that n plus 1 has become an n. Minus 1 to the n, 1 over n factorial is the last term. Okay, so let's just check. For example, D3 is 6 times 1 minus 1 plus 1/2 minus a sixth, which is to say 6 times 1/2 minus a sixth, which is indeed 2. And D4 is 24 times 1 minus 1 plus 1/2 minus a sixth plus a 24th. And if you work that out, that's equal to 12 minus 4 plus 1, which is equal to 9. Good. Okay, before I go on, I have a little digression here on some elementary set theory. So suppose we have a set S, which is a subset of another set X. The complement of S is all of the elements not in S. I'm going to write that as S bar. S bar and S upper C are two standard notations. So the picture is we have this set S, and then S bar is everything outside of it, so that X is the disjoint union of S and S bar. And I want to look at what taking the complement does when you have two sets. So suppose we have two sets, S and T, and sitting inside X like this. And I'm interested in the complement of the union of S and T. So if I take S union T complement, what do I get? Well, it's this region out here. And what is it? Well, if you think about it, it's S bar intersect T bar. So the elements which are not in S or T are the elements which are not in S and not in T. And that is to say that taking complements changes unions and intersections. That's the key point. So this is an elementary fact, but I suggest you stare at this picture and convince yourself that this is correct. Complements change unions and intersections. And this repeats, of course. So if you have the complement of the union of n sets, that's the same thing as the intersection of the complements. Okay, so I want to apply that to my inclusion-exclusion formula. Suppose I have these permutations. Si is the permutations such that number I appears in the correct place. Then the derangements, what is the derangements? The derangements, if you think about it for a moment, it's the intersection of S1 bar and S2 bar and so on. It's the permutation such that 1 is not in the correct place, and 2 is not in the correct place, and 3 is not in the correct place, and so on. So the derangement number is the order of these intersections. And so, in other words, dn is the order of S1 bar intersect S2 bar intersect dot 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 Sn bar. And by the discussion on the previous page, that's the order of the union, the complement of the union, which is n factorial minus the order of the union. And this is just saying in formal set theoretic terms what I explained earlier about dn plus nn adding up to n factorial. So I haven't really said much new except that I can now restate the inclusion exclusion in version 2, which is the following. It talks about intersections of complements. It says that if you have a bunch of sets S1 through Sn, then the order of the intersection of the complements is the order of S, which I forgot to say these subsets are all a subset of a given set S. It's the order of S minus the sum of the order of the SIs plus the sum of the order of intersections of pairs, and so on, down to -1, plus or minus the order of the intersection of k of them, all the way down to -1 to the n times the order of the intersection of all n. And this first term, again, this S is where I'm thinking of S1 through Sn are subsets of a bigger set S. So that's where you're taking the complement. Okay, that's all for now.